going to let you announce the people. I can't even pronounce their names. So.
Let me see. I'm also not so familiar. Tuesday.
Colbacini,
Corbacini and Sid Ahmed.
Sid Ahmed,
And you.
Okay.
Okay. And about the poster, there will be a queue, and then each person come here and talk, and then change. So
Okay.
perhaps we don't need to
Say anything, yeah. Do we have to write anything up about the posters, as far as the write-ups? Do we have to write up anything about the poster?
Sorry, I couldn't get.
Do we have to write anything about the posters?
Yes.
We do have to write
Poster
the posters as well?
Yeah. So perhaps the best way is to look around the poster and catch the highlight.
Yes.
Yeah, 3 to 6.
Okay. Because there's, 23 posters? How many other, are they all coming up here to?
Yeah.
Okay. How are we doing? Okay. Should we start? Are you ready, sir?
I think so.
Okay.
Could you please?
All right.
Can you?
You want me to start?
Yeah. Yeah. Can you start?
Sure. Sure.
Thank you very much.
All right, we're still waiting for one of our colleagues up here, Dr. Jay Zuka, but we're going to go ahead and get started if that's okay with everyone. And so I want to welcome you all to this session on network optimization, very close to my heart as well as to the other panel members. And our first presentation is Adaptable Turnkey Solutions for Infrasound Stations by R.J.Y. Colbacini. Would you please come forward, and we'll start off with our first presentation. Welcome.
Thank you. Hello, everybody. My name is Rémi Colbacini. I'm a French guy, and I work for the French company called Enviro. So behind, this is a famous mountain from our country, the mountain many times painted by Cézanne, close to Aix-en-Provence. The company is based in Aix-en-Provence. I will present today my work. This is the work of my colleague Clément Bennoravitch and Pierre Chamberger too, called Adaptable Modular Solution for Infrasound Station. So, why Envirus is so involved in infrasound? Envirus is an EPC company. We are doing like engineering, procurement, construction related to monitoring and renewable energy. And for many years now, we've been working with CTBTO, and we are grateful and thankful to CTBTO to have this opportunity to to make all this operation and maintenance mission on the IMS network. So this is a map of all the stations we've been working on, we've been sending equipment to. And another part of our job is we have today 3 operation of station. This is the green label, the dark green label. So we got Santa Helena, Tristan da Cunha, and Capo Verde. So from all those missions and this work, we've been we acquired some like infrasound knowledge, and we developed industrial skills, so that today we have many work tasks and workforce with CTBTO related to infrasound. So we manufacture and we supplied a lot of infrasound equipment, so mainly volt and WNRS, but also power and communication items. We also do a lot of troubleshooting and maintenance mission. So all those missions and all this work with CTBTO and with, especially with the PTS made us better, and we acquired more skills about infrasound. That's why today I will try to summarize all the work we've been doing with CTBTO and explain how today we kind to develop a modular solution for infrasound station. In all the presentation, you will assist in SnT or ITW, ADU. We are like talking a lot about the event and the quality of the signal. The signal is really important. And what I'm today want to present you is what is between the two. Like how, because the quality of the signal is really important, but if the station is down because of maintenance, because of power issue, you don't have any data. So that's why today that's why also Envirus is working on making like a reliable and long-term station. So I'm going to give a few examples of infrasound station. This is, for example, a piece of infrasound station. If you put it in a network, it's a portable station we've been developing with the manufacturer of a microbarometer called the Sismowave. It's also a French company. So this is a portable station time. So you have all the assets, all the sets of infrasound station. You've got the power system is a small battery inside. You've got the sensor. You got the digitizer inside the sensor, and you got the wind noise reducing system. I will talk about this later. This is also an example of infrasound station. This is a acoustics test we've been doing at our facilities, comparing the signal from our wind noise reducing system and a microbarometer connected to only one filter. And this is, of course, a great picture of infrasound station. This is taken from IS-41 in Paraguay, in Villa Florida. Envirus, we made a great job of upgrade last year, providing some equipment, and this is a picture of the final results. So now I'm going to explain what composed an infrasound station by trying to make like explanation by modules, like trying to divide each part as a group or a group of specification. So the main part, of course, of the infrasound station is the sensor. And as a puzzle, we will add some set like the digitizer. Sometimes we get both inside, like the MB3D from Sismowave. So then we'll have the communication system, the power system, the WNRS, so the wind noise reducing system. You need an enclosure for all this, the volt, and that makes an infrasound station. And of course, you can add some option and important asset too, like the meteorological box, or CTBTO is asking for authentication module too. Now they are more and more asking for reference system to compare the signal from the Windows system to the signal without, and also like for sure like some surge protection devices. So first, before selecting any models, you have a lot of criteria that define the environment of the station. So you will focus of a band of interest, a frequency band, like the CPTO, the PTS has his own like frequency band request. You will focus about the environment. You will choose a array design, doing like I don't know, a threshold of the detectability, or then you will think about the use of the station. Is it a temporary service station or long-term station? You will choose also the type of maintenance. You will have the opportunity to go every week or no, like in Antarctica. And then all the criteria will help you to choose the modules you want for the station. For now, for the presentation I'm doing now, because I'm more presenting the work of my company, is more about a long-term station. Of course, I can do an infrasound station, putting a Raspberry Shake, I don't know, like a small, but I'm more about talking about a long-term research station. And we've been working with CTBT with the IMS network. The first module, it's the Volt. So the Volt, it's a word that I've been learning with CTBT. I didn't know this word in English before. It's an enclosure. So we work on different aspects of the Volt to understand how we could adapt the Volt to the environment. So we choose, we selected, we tried to find a good insulation, we tried to find the good dimension, the good weight, because sometimes you need to carry the Volt to the place, to the site, and also to make the better and the best interaction with other modules, like the way we put the box inside, the way we connect all the pipes, etc. And we came out with a selection of a few Volt we developed in our facilities. So this is the first picture. It's a light panel sandwich solution we installed in Galapagos, IS-20. So the criteria really important for those Volts. We needed small boxes and really light, but also like a UV resistance and let's all summarize, and easy to customize. So we came up with a light panel solution. It's a good solution, and you can it's suitable for sensor box, or if you want to put equipment Volt, or you can also choose a big one. We put all the equipment inside. Another solution is a Pelicase solution. This is a on-the-shelf solution. You can find easily Pelicase on the market, but we developed like some passage cable gland to optimize the way we put it on the sides. And the last solution, so this is me trying to open the Volt. It's the heavy-duty solution. It's a stainless steel solution with insulation, and it's perfect for the harsh environment. This is a picture of the model we are sending to Bariloche. So Bariloche is the next infrasound station of the IMS network. WNRS description. For those that don't know about the WNRS, this is a mechanical filter that will decrease the ambient noise for the sensor. So we've been developing with a CTPTO 18-meter span model. This is the one now I think the PTS tried to implement in every station. And we also try to find the best material and the best way to build this WNRS, trying new way to make the pipes and doing some tests, so UV tests, acoustics tests, and we came out to two solutions. So the stainless steel solution. So this is a picture of Diego Garcia, the upgrade installation last year. So this is a stainless steel version. And the other version is we developed it because it was an easier way to install it, and it's really how can I, friendly with the environment. So this is a whole solution. So you can put your WNRS in forests across the trees, and it's a really cool solution. So those are the two solutions we are developing now. For example, the one on the right, we install it in Galapagos, in Tristan da Cunha, in Chatham Islands. The power system, so there are many possibilities for power system. And when you look at the IMS network, you can find many solutions. We try to summarize our work in two cabinets, in two solutions, the on-grid and the off-grid solution. And we developed this standardized cabinet with a solar MPPT cabinet, so it's an off-grid connected to solar panel and a battery rank. And on the other hand, AC-DC cabinet, so when you are grid available and you just want to convert the AC to DC. So, and then on those two cabinets, we've been doing some tests, and now we are trying to develop a global monitoring solution so we can check voltage and current, etc. And that's the two boxes we've been developing with the help of CTBTO. So one is for grid available, so you put AC close to the site. So this is example of IS-40 in Papua New Guinea. So this is connected to battery rack, and we had some AC plug option, integrated LPD. So this is solution for on-grid, and the off-grid solution. This is example of IS-41 in Paraguay. So same, you have the backup solution power with the battery rack, and we had some now we have some monitoring solution and also LPD integrated. Same work with the communication system. We tried to standardize our offer, our box, and we developed a media converter box. So the media converter box will be connected to the solution, the technology solution you choose. So, or it's for now, we are more and more focusing about radio communication or fiber optic communication, and so the media converter will convert the signal from. Not convert, but we'll take the signal from the digitizer and send it to the solution you choose. Will be connected to the splicing box if you choose a fiber optic, or to the radio modem box if you choose a radio solution. And this is the summary table. So for every set, you will have many options, of course. I put etc., but I don't want to frustrate anyone. Of course, there are many other sensors, but it's just a list of ideas of possible solution. And so just to show you how we are thinking the infra-sensation now, like more about modules. And so when we talk to new infra-sensation with people, we try to say, okay, what about what did you choose for the power system? What did you choose for the digitizer? And we build like this the station. So let's build together the station. So it's the famous sentence from France, à la carte. It's perfect for this presentation. So we'll choose, for example, first the sensor. We will, of course, choose. I will choose, of course, my partner, because it's we've been doing working a long time with them. So, for example, the MB3A. Then I will add, for example, I choose Geotech, but you can choose Google or Nanometrics. Then the two media converter boxes connected to the grid and connected for, why not GSM, the volt, and at the end, the WNRS and the installation of the whole system. So this is the work we are doing now, and we are trying to go forward, like to get all the modules divided and to make more and more like specification of each model to be able to answer and to adapt to every kind of environment. So thank you for your attention.
Any questions? I have one. I like your approach. The modularized approach is a very good way to go. Was there some way that you captured your trade-offs so that you can go back and define why you picked the things that you picked as far as the different modules?
Which one?
For all the different modules you had, you obviously made a choice.
Yeah.
So did you capture that methodology you used for that module for why you?
No, it's more by experience. Like, yeah, it's more asking my colleagues and trying to understand why in the past people they chose this solution. So it's more by experience. Yeah.
And so, my suggestion to you is in the future to capture that, because that's very important. Experiential type of information is great, and for optimizing solutions, we want to be able to go back and capture that. So that's a phenomenal job, but that's the next step probably, is to capture just why you picked the different things in the modules you did.
You're right.
Please.
With your WNRS, do you have a lot of seismic? Sorry. With the WNRS, is there a lot of seismic coupling through the tubes before you get to
We try to avoid by putting some support that we put some rubber on the support. So this is the goal of this support, like to avoid like that all the system doesn't shake. But of course, yeah, we have some coupling with seismic wave, yeah. Especially with the host solution is laid on it's on the ground, like so.
I have a follow-up question from the first, and that is, do you collect data after installation to help you assess the equipment as you look to the future? For instance, with on-grid and off-grid power, do you see a difference in the reliability?
The thing is, like, this work is, and we are thankful for that, like in collaboration with CTPTO. So it's more about like when CTPTO has like some remarks, and we take these remarks into account, and we say, okay, that's a good point for the future. We won't use this solution because they are self nodes. I don't know, like numeric self nodes. We tried to propose, like for example, a new charge controller, and we tested, and it wasn't good because it wasn't in the criteria of CTPTO in terms of nodes and etc. So yeah. But it's more about like CTPTO getting back to us, saying now there is a problem with this charge controller or something like that.
Any other questions? No? Well, thank you very much. That was a great presentation. All right, now we'd like to have the second presentation, the latest development of the standard station interface calibration module by Waisid Hamed. Welcome.
Thank you. Good morning, everybody. So my name is Yassin Sid Ahmed. I'm working at the IMS division and engineering and development section. And my slides will be about this SSI calibration module. And SSI stands for Standard Station Interface, and is basically the software that we install at station that collects and forwards the data to the IDC. So first of all, the requirements that are defined in the operational manuals, some of them are specifically defined for calibration, and among them we can see that there are requirements for the on-site calibration, and more specifically on-site calibration in use to do a QC on the instrument stability. And by stability, we mean having the behavior of the system within a plus and minus 5% corridor regarding what is expected, what we call the nominal response. So we have to monitor this over the full IMS passband, and the QC has to be done at least on a yearly basis. In parallel, we have also requirements regarding the planning and communication of calibration activities. First, at the network level, we would like that all stations are calibrated, but not all at the same time. So this requires some planning and allocation of specific time slots for each station of the network. And then communication is needed at the station level to between the PTS and the station operator in order to define these time slots. So what are the challenges? The first point, and I think it's the main one, and some other challenges are related to this one, is the high number of sensor and digitizer combinations in the IMS network. So the heterogeneity of the network brings some challenges because we will have to face different situations with different hardware, different software, and we'll have to put some efforts on procedures and training that will be multiplied by the number of combinations we would have. So as a consequence, there are significant resources that are needed to train station operators. With this heterogeneity, we have a higher variety and of complex hardware and software issues. And also, we have other challenges that are related with the requirements we have, that is to provide a full frequency calibration response in an IMS 2.0 format. And finally, the last challenges is related to the command and control requirements and authentication of messages. So on-site calibration is a complex and technical process that is involving different tasks and people. I just took some of them. This is not extensive, but the only point is to maybe to show that usually we use the simple word calibration, and without giving more details, people usually think about performing the calibration task, which is injecting the signal and getting back the result. What is interesting to see is that behind you have many different tasks. So as I said, it starts with the initial planning at the PTS. All the communication between station operator and PTS is really an important work as well. Then, of course, there is this calibration task that is performed at the station and might vary depending on the equipment that you have. There is the result review that I like to decouple from the calibration task, because this review might be straightforward or not and really involves the expertise of the station operator. There is the formatting of the calibration results into this IMS 2.0 messages, the update of the CD11 stream by the station operator. And after all of this, once the results are received at the PTS, there is this validation and publication phase that is also very important. So now that I've summarized the requirement and the challenges, I can say a few words about how these were addressed. So at the PTS, there are significant resources that were used to resolve these challenges, and I can name this CAMT software. So CAMT stands for Calibration Activities Management Tool, and is a software that semi-automatizes the planning and scheduling, so this initial part. And this CAMT also supports station operators for the validation and publication phase as well. So the idea is to have a platform that where we can reach all the different information and also store the different communication we have and results. So this is for the first and last part. And in the middle, of course, we would have to perform the actual calibration task in order to get these results. And to compensate, I would say, or to address this challenge related to the heterogeneity of the equipment, an SSI calibration module, so it's a piece of software encompassed in the SSI software, has been developed in order to provide a standardized and friendly, user-friendly interface to support the station operator to perform the calibration, to interpret, to get the raw results, to have a support to interpret these results, to format the message and to send it to the IDC. And of course, along with these two softwares, training materials and training are also something that is needed. So the features of the SSI calibration module are the following. So first of all, it's important that this software is compatible with the calibration operational process. And all the other features are related to the requirement I have presented a bit before. So it, of course, has the possibility to build this IMS 2.0 format, including the full frequency response, and to send it to the IDC. It allows messages to be authenticated, because this SSI has an authentication module that can be used. So as I said, this module aims to make it possible to define, perform the calibration, review it, and to report it. The idea is that it's compatible with different combination of sensor digitizers. And another important point is that by user-friendliness, we think also about having the station operator the possibility to just access a user interface from a local computer that will be connected to a remote computer, and every click would be actually sending a command line through the network. And having this approach is effective and is something that you like to have in the case of low bandwidth. So there are different user modes with this calibration module. The default one is the semi-automated one, because we would like, the best approach is to have everything being verified by the station operators, because first of all, a QC is always something that is interesting to have, if not mandatory. And the second point is that the station operator, the person that will perform the calibration, is the person that has all information in hands. He knows his station, he knows the conditions under which the calibration will be performed, and this expertise is also something that is needed at the time where the results would be reviewed. So in this semi-automated mode, the scenario from the PTS is received at the station through this module. If it's accepted, then the calibration is scheduled, then performed, and then the results are reviewed by the station operator before being sent. In parallel, there are two other possibilities. The first one is the fully automated mode, where the calibration module will receive the calibration scenario and everything would be performed. So according to the schedule that is put in the scenario, the calibration will be performed, the result will be automatically computed and then sent to the PTS. And then there is the manual mode that is needed in case of unscheduled calibration, for example, or in case of testing, when you want to have a control of each of the steps. Currently, the supported hardware are for the digitizer, the Guralp DM24, the Nanometrics Europa T and Europa HRD for these two models for the Europa, and the Quantera Q330HR. I could have added the Guralp Affinity here as well, as it's fully compatible with the calibration module. And with these digitizers that are supported, a certain number of sensors have been tested. So the CMG3T from Gurab, GS13, STS2, which, and you have a list here of all the tested configurations. Just to give an overview, I will show some screenshot of what you can expect to see when performing a calibration on site. So I'm only showing this user interface. So basically in the background, there is the main SSI Calib view where you have all your calibration that have been performed. And when you click on one of them, you have the access of this window called Calibration Group, where you could have a group of calibration that you would like to be performed. So here we have taken the case of a classical 3 hours random calibration plus a 5 minute sine wave calibration. And here you can see that you can have as many calibration as you would like, and you can schedule them as much as you. I mean, there are some flexibilities, and this is something that is interesting to have in case of seismic arrays, for example, when you want to schedule a high number of calibration. So by clicking on your calibration, you would get 2 additional information, more detailed ones on your signal. And here, for example, by clicking on the random calibration, you would see which channel you're calibrating, what's the amplitude that you're using, on which frequency band the signal will be computed, etc. And at each step, you have also the status, and you can follow if your calibration is either successful or has been problematic. And if it has been problematic, you can track the place where this has failed. One of the features that is interesting to have is to display the output signal from the calibration, and this, with also the expertise of the station operator, is very important to review the calibration results. For example, you wouldn't like to use signals that have been polluted by an earthquake or by unexpected vibration to review your calibration results. Also, it's also interesting to check whether your signal have clipped here and there during the calibration. I think it's the last screenshot, because this one is the response view window, which where you can see the calibration results plotted against the nominal. And if you zoom, you can see this plus minus 5% corridor. And this way you can graphically having a very quick overview on your calibration result. So the IMS 2.0 messages is automatically formatted either using FAP or poles and zeros format. And about the latest updates of the module, there is this smoothing function that has been implemented, offering the possibility to send the result using poles and zeros. We are trying more and more to roll out the SSI software, and especially the latest version that encompasses the calibration module. And for the beginning of 2019, and with the support of station operators, we have successfully installed and calibrated KEST, which is a 3-component seismic station, and also ARCES, which is very interesting because it's a 25 element array, and this was a nice stress test for the calibration module and its scheduling. So in conclusion, the idea is really the data monitoring data quality over time through the introduction of standardization through this SSI calibration module of heterogeneous equipment to be tested. And if I could summarize it in another way, what would be or what is the real added value of this module is to go from a phase where we spend significant energy into the calibration task to a phase where we would use a higher and higher portion of this energy into the data interpretation and potential troubleshooting whenever they are needed. Thank you.
Are there any questions? Please.
Yeah, my name is Josphat. I'm a station operator, PS24. I have two questions, one generic and the other one related to SSI calibration. In PTS planning, I think one of the challenges we face is the calibration definition file, because you don't know beforehand which definition file to use. So you go to the station, it's 2019, for example, you are told you should use the file of 2016. I think that should come beforehand during the preparation process. Then the other issue is if I am able to remotely log into my station from my NDC, for example, is it possible to use the automated user mode for the calibration? Thank you.
Mm-hmm. Thank you for your questions. So for the first one, I think that is related to the planning and the definition of your calibration. Usually at the beginning of the year, there's a message that is sent that explains how calibration would be performed, and with this email you have information on the nominal that you would need to use. So I'm not sure if this is what you are referring to by calling the calibration file, but if this is the case, it's an information that you have beforehand, and then whether you need some support to use it, I mean, this could be a possibility. I would like to say that with the use, because this calibration definition might be related to a specific configuration file pertaining to a specific equipment. And with the calibration module, we do it differently because we create our own configuration that would be handled the same way for all the different stations. And in that case, you spend some time once for all to configure your environment, and then from one year to another, you go to the user interface, you do a copy-paste of your calibration performed from the previous year, you change the schedule to adapt it to the current year, and then you're good to go. Your second question? The user mode, yes, thank you. So yes, so you can definitely you can definitely perform the calibration remotely from an NDC. ARCES was done this way, for example. I would like to recommend using this semi-automated mode. The automated one is really when there is no other choice, because you take different assumptions when you do it. With the semi-automated one, you have control points where the station operator brings his expertise and reviews the message. I hope this answers your question.
Thank you very much. Yeah, there may be other questions, but the time is, we are under time pressure. So if you have questions after this session during the coffee break, please talk with the presenter directly. Thank you very much.
Thank you.
So at the risk of kind of breaking normal protocol, I'm on the panel, but I'm also one of the presenters, at least the beginning of a presentation, so I apologize for that. So the next presentation is on more mission, less money, and we're really talking about optimization here in this panel discussion. I'm David Merker, and I'm the director of the U.S. National Data Center, and I've been in that position for about 10 years now. And so, oh, here, I'm sorry. So, as we built the U.S. National Data Center alongside of the IMS stations, we've been in a building mode for quite a long time, and we've had a lot of operational successes along with the IMS system of the CTBTO. And this has been a very challenging thing for the United States, as it has been for the CTBTO. But you find yourself building in a total different way with a new system as you do with sustaining it. And so we're getting to the point where the Comprehensive Test Bench Treaty Organization and IMS is right now, is how do you optimize from the point of you've got a system out there and you want to make sure that you can sustain it at a reasonable price, but also be able to support the great work that comes out of SnTs like this. There's obviously technologies that are moving forward and capabilities that we want to include in our systems, so we don't want them to be stagnant. So what we're finding is that we're entering in a stage now of truly optimizing and fine-tuning our systems analytically and utilizing all the analytics that could be possibly made available to us on our systems, how they're performing in the field, how we're performing maintenance, how we're standardizing, those kinds of things. So I'd like to introduce two of my colleagues, Mr. Robert Martin and Steve Poindexter, to go into a little more detail about how we're optimizing our systems.
Thank you, sir. So, as Mr. Merker presented, we have historically invested in expanding the robustness of our system design. And it's quite simply investing in power and infrastructure and grounding. And through that, we've quite simply we've been successful, and we've seen consistent data availability rates in excess of 98%. And so what we're realizing now, however, is that we're no longer receiving the same return on investment that we once were. Our dollars now no longer buy us that same gain in performance. And so we've now shifted from what we considered, what we called a growth model, which was really improving and speaking to operational capability, into a sustainment model. And part of that sustainment model is managing the total life cycle cost and making sure that we're appropriately managing the trade space between our inherent availability of our system and our operational availability. But that trade space requires that we take a new strategy and have a new approach. So to develop that new approach, we're essentially asking ourselves three key questions. The first question is, what should our system do? And this speaks to the requirements that we're trying to fulfill by fielding our network. The second question is, what should our system, or what does our system do? And that speaks to the operational capabilities. How are we actually performing? And then the final one is, what can our system do? And what can our system do speaks to the inherent availability of our system and the theoretical limit of how we can perform based on the robust nature of our current design and configuration. And so ultimately, this business strategy, this operational organizational strategy, is about managing that trade space between inherent and operational availability. And it also gave us a very effective framework for testing the multiple life cycle variables that drive that trade space. Under our growth model, our paradigm was essentially we were buying more capability, more mission, more money. But as we shift now into sustainment-focused optimization, we're identifying the question, how do we get more mission for less money? And so finally, I think something very important to speak to is that for a long time under this growth strategy, operational availability was undeniably our guiding metric, right? It is where we focused all of our attention. It's where we vectored our energy. But as we transition now to sustainment, it's important to understand that this is no longer sufficient as a key focal metric, that to see faster and to see further, we need a new set of tools. And what I mean by that, what I mean by a vanity metric, is quite simply that data availability tells a story, but in the sustainment tale, it doesn't tell the full story. And in fact, by focusing on that exclusively, it can become very misleading and not reveal some of the vulnerabilities or ways that we can optimize our system. So with that, I will turn it over to my colleague, Steve Poindexter, to speak to some of those approaches.
So as Rob mentioned, data availability isn't enough. We're looking for metrics that are actionable, that help us control all the elements of the life cycle for us. So on this next chart, these are just some examples of our dashboards. It's not meant to be an eye chart, but just quickly and visibly looking at this, it starts to tell me things I need to do. For example, under our network diagnostics, we plot out our data gaps now over time throughout the calendar year. That's a plot of the top. And also, the chart underneath it, that is an example of area and time blown out by day. And clearly, there's things going on around the 10 and 100 second framework. And if we just looked at the data availability, that's Chiang Mai, and it was running around 99.4% data availability. You would never recognize that there is an issue. So digging deeper, we quickly were able to assess that we had an issue with radios. We reconfigured the settings, and the issue went away. For maintenance actions, we have been tracking each and every one of our maintenance actions over the years. And what we start to understand on the horizontal axis is how many times the maintenance actions are occurring. We're also then seeing on the vertical axis what the impact is in terms of cost of network hours of performance. Using that data, we're able to do probability plots of when we expect these issues to happen or failures occur, and we're able to derive a preventative maintenance strategy around what we want to do. This helps us to control the variance in our network. Finally, on the end, we have a picture of our inventory health, and what that is using the CTBTO tool in collaboration with them of vMetric. It gives us a quick visual of inventory that's required to support the stations. All the locations are on the right, the parts are up on the top, and the red indicates a deficiency in terms of the number of parts that are required. The bottom half is our actual inventory at our depot and field locations. And finally, on the bottom in red, it highlights for us what the quantity of parts are to buy and how much it is to get them. So in a nutshell, that chart tells us what to buy and where to put it. It's very powerful. Another area of the life cycle that we found that people often neglect is our resources. So under Mr. Merker's direction, he's charged us with our existing engineering resources to support more. Historically, we've only supported the waveform side of the house, and now we're transitioning into supporting the radionuclide programs as well at AVTEC. And we've been able to do that in a couple of ways. One is by looking at the overhead rates and controlling the actions that we actually work on that bring value to the programs. Over time doing this, we've been able to steer away from non-value added activities and just focus on the work at hand. Another method that we did, so now that we're getting back more labor that's going to value added work, we can redistribute that. Another way we did this was by tracking the work. On the next chart down, the blue represents the waveform programs, and you can see the trending or the allocation of engineering resources going down. And then for the radionuclide side of the house, it's going up. That could be good or it could be bad. In our case, we've done this very deliberately in a controlled fashion to where there's no impact to performance on the waveform side of the house, because that would be a failed experiment by my estimation. So there's no impact, and now we're able to give resources over to our RN side of the house for those programs. In the bottom chart, what you see is a current distribution of our resources between waveform and RN. It's about 60-40. What is really nice is we have that bounded in a way where it's in a sweet spot. So based on program need or other direction, we can quickly vector those resources and assign them to where they need to be. Okay, so now that we're getting some interesting data points, it's starting to tell us what is value in our network. So mainly, we've been focused on a site strategy in the past, but as we bring it up to a system level or network level, we start to understand the individual sites in terms of what capability do they give you in terms of coverage. Also, we obviously want to understand the cost of the sites. What is it to design, install, and maintain those sites? From a risk standpoint, we certainly need to understand the probability of failure, how often they fail, how they fail, and finally, when they do fail, what is the impact of the failure in terms of data, downtime, the variance, and ultimately potential capability loss in the mission. And probably to me, the most important parameter is when you're trying to figure out where you're putting your budget and what you're doing is, what's the utility of the site? What has it actually contributed to in terms of event detection over the years? So in conclusion, AFTEC has kind of shifted towards a more value-oriented culture where the things we choose to do are done in a way that bring value to our customers and our organization. And along that theme, we've been able to reduce our maintenance footprint, being able to pull technicians back from the field to assign them to other activities as needed. And implementing this predictive maintenance approach has allowed us to increase network performance by strategically understanding the variability of the network and controlling that. So our overall network performance as a whole has gone up. The thing I'm probably most proud about is our reduction of inventory holding. So currently we look at what it takes for 5 years of parts to sustain the network, and where we're at now from where we started, we've decreased that by over $10 million. It's absolutely amazing. And all of that money is able to be reinvested back into other areas. More importantly, moving forward, as we get more mature of this, we might be able to reduce the 5-year window down to, say, 2 years or 1 year. By holding less inventory, obviously it's cheaper in terms of buying the parts, but now we don't have to pay to store them as well. And finally, effective resource allocation. We're able to literally control what our workforce is doing, what they're working on, and basically provide accountable stewardship to our taxpayer dollars. So implementing this type of methodology to our lifecycle management framework at AFTEC, in summary, has literally given us more mission for less money. Thank you.
Are there any questions?
Thank you, Steve. You mentioned some of the tasks going forward. I'm interested in some of the challenges you face getting to this point. I assume there were quite a few because there's a change in culture and stuff like that. So.
David, that's the biggest part, was the culture change, because, we've talked before, there are tremendously smart individuals that work in our organization, your organization, and people know things, but as you start trying to quantify that, you start to realize the data tells you a story. And as we move forward with data-driven business decisions, you start to realize, I have to have the data to justify things. And that literally, so now that we've gotten to the point culturally where we're collecting the data, it starts to go into the face of commonly held themes by individuals, and just breaking that down and trying to execute it becomes a challenge.
So the other things that you find that are not intuitively known from my standpoint is things like inventory. Inventory to me always was satisfying. To have things on the shelf, I felt I was comfortable that I could sustain things. But what you find is that as you increase reliability in the field, things sit on the shelves too long. And now you start having, by having too much resources on the shelves, your reliability goes down. And it's almost anti-intuitive, and it takes a change in culture. You want just the right sizing, what you have in the field, what you have back home, what you're fixing, and what you're throwing away even. And the analytics really change your mind on how you do this maintenance over a long period of time in the long haul. And you know this at home. You don't keep parts for your refrigerator. You don't keep parts for your stove. You get them as things break. You bring things in, and you get new parts. And we need to start getting into the same culture that most of us take in our household lives, and the way that we maintain our cars and that. And like I say, I'm part of the cultural change. Things that made me feel very comfortable in the past time was the biggest problem that I'm finding today that I need to resolve by changing the way that we do our thinking. And analytics and system engineering, which is the next discussions we're going to have, is the way to go. You really need to look at things completely from beginning to end in a system engineering approach, and you'll find all kinds of magic out there. And this is going to be it's a secret for us to sustain such a big network. And CTBTO, I think that's the secret to stay viable for the next 50 years. Any other questions? Well, thank you.
Thanks.
Thank you very much.
Yes, please.
Thank you very much. And now we switch to the poster preview session. And today, total 10 presenters are gathering. And I call the number of a poster. Please come and gather with us in front of the stage. Poster number 9, poster number 10, poster number 13, poster number 14, and poster number 20, poster number 23, poster number 24, 27, 32, 33. Could you please come and join us? Each presenter has 1 minute to explain about your poster. And after the end of 1 minute, our colleague will sign. So then please give the stage to the next presenter. One. Okay. One more time, I call the number. Okay, poster number 9, 10, 13, 14, 20, 23, 24, 27, 32, 33. Okay. Okay. So, okay. Total 5. Okay. Now, 5 presenters are here. So, yeah. Yeah. So, let us start. Please, poster session number 9.
Good morning, everyone. I am Jairo Villalobos from Costa Rica. I work in Volcanological and Seismological Observatory in Costa Rica. Very fast, my poster is an integration of seismic volcanological network with our NDC in Costa Rica. I don't know if you can see very well here our network. We have a big one network, maybe 80 seismic stations. We have some events per year. Maybe the last year we have 9,000 events, maybe 200 seismic event field with the population. And in the picture in the center, we have an integration of Antelope acquisition system with SEISCON in the NDC server. And in the last picture, you can see the waveforms. This is the portable infrasound array developed in November the last year. We can capture 1 meteorite in April 23. Thank you.
Good morning. I'm Bernd Wernsberger from the PTS. I'm presenting in my poster the implementation of a QA/QC program for the noble gas network. At the moment, we have 25 noble gas stations operating in the IMS network. In order to ensure their high performance and the high quality of those stations, we are running a QA/QC program. Basically, this consists of introducing a known activity mixture of xenon isotope into the systems during a normal operation. The system measures the radioxenon mixture. The final sample is archived and being transported to radionuclide laboratories for remeasurement. And finally, we are comparing the results of the station measurement with the laboratory measurement, and we are counter-checking also with the original data sheet of the radioxenon spike mixture. And this allows us to perform some QA/QC measurements to implement those QA/QC program. If you're interested in my poster, I'm happy to see you there.
Thank you.
My name is Marta Galindo. I am working for the Organization of the Prohibition of Chemical Weapons, and I am presenting an application, in this case for the optimization of the performance of the OPCW verification system. The idea is to use knowledge management. Here on our first presentation, we have addressed a question of how to codify the know why. This is how the organization has this knowledge, and I am presenting an application where, using the optimization of the process-oriented knowledge product, we can improve the way how we are working. So if you are interested, either on knowledge management per se, is a subject that usually calls the attention of the people, please come and visit poster 14, or if you want to get our lesson learned that can be applied to any process-oriented activity, just come and we can discuss it. Thank you.
Thank you very much. Next presenter, please.
Good morning. My name is Peter Davis. I'm here representing the IRIS USGS Global Seismographic Network. The subject of our poster is the steps we are taking to improve both the quality and breadth of scientific data we are collecting at these stations. The interest in this body is that approximately 50 of our stations are also IMS auxiliary seismic stations, so this is very pertinent. Two of the steps we are taking to improve quality is to replace the primary sensors at our stations with more modern instruments. We present evidence of the improvement in the quality in our poster. A second subject is the new installation techniques we are using to improve particularly the quality of our horizontal data to reduce the effects of local tilt. And finally, we are increasing the breadth of the data that we're collecting in our stations by introducing infrasound sensors in our network, approximately 10% of the network right now. Look forward to discussing it with you at the poster.
Thank you.
Thank you very much. Next presenter, please.
Good morning. I'm Dennis Bustillo with General Dynamics. I'm here to present my poster on parallel processing and optimization we did to our pipeline, our data processing system. So we had a system that was hard to maintain and deploy. And so what we did is we took the software and we broke it apart into individual modules. So it became a modular approach and almost microservices. We took this and then we were able to expand, build in redundancy to our system. And it's also easier just to deploy new functionality, new software updates, take systems down or services down and bring new ones up as needed for data processing. So overall, it improves our redundancy, uptime, improved capability, and overall DevOps functionality. So thank you for my poster, and I'll be available if you'd like to discuss some more and our techniques that we used. Thank you.
Thank you very much. Next presenter, please.
My name's Eddie Tillestrand. I'm also at General Dynamics. So my poster covers two things that we're testing at our stations. They're both related to power. So the first one is we're testing basically our standby generators. When power goes down at our radionuclide sites, we need our generators to be ready to keep our detectors cold. So we've implemented new monitoring tools for those generators so we can know that they're going to work when we need them. The second thing is a power quality testing that we've been doing. So when we have parts fail and we blame the power at the station, sometimes we don't have any actual data to prove that. So we're trying to get that data so we can know when parts fail, was it the power quality or was it something else? So if you have any questions, come see me at the poster. Thanks.
Thank you very much. The whole menu of this session is over. So, yeah, I would like to switch to next session. Thank you very much.
Yeah. Okay, thank you. We're behind. No, we're good. We're good. That's okay.
Give them 1 minute to just reorganize themselves. So it's Mark Harris, isn't it? It's Mark Harris?
Yes. Oh, thank you, sir. And I'll get you my notes.
No worries. Yeah. Just that one. It's me. I have no idea. I've tried to communicate with the guy for the last 6 months and no show. Yeah, just leave it here, yeah. Mark Harris. Can one of you guys get Mark Harris?
Yeah, it should be.
Yeah. Okay. I'll be recording. Yeah. We're going to go a little bit over. If we're 5-10 minutes over, it's no big deal. Yeah. We'll just go with the flow. Okay, let's go for it. Okay. Alex didn't sit down. Hey, Danny. I'll get these guys to sit down.
All right. So you're going to introduce the speakers now?
Yeah.
Good. Jay owes me big time.
Yeah. Thanks, Dave. Okay, good morning. We'd like to start the session on systems engineering. This session is a good segue from the network optimization. It's a good segue into the systems engineering, especially the last presentation that we heard. And systems engineering is an interdisciplinary field of engineering and engineering management that focuses on how to design and manage complex systems over their full life cycle. And we've got 3 talks today, and they're going to talk about 2 complex systems. One is the IMS network, and the other is the IDC re-engineering effort, quite substantial complex systems. So without further ado, I'd like to start with introduce the first presenter, Danny Foster, who works here at the CTBTO.
Thank you. And I have this, and the pointer is
Mark Harris.
That's what, yeah, cool. Okay, thank you. So, good morning, and thank you. My name is Daniel Foster. I'm from PTS and I work in the IMS MFS section with my colleague Peter Benixek. And I'm here to talk to you about our recent work on supportability analysis and how using something like the CRISP-DM framework might be helpful to us in our work. So, by way of reminder, the IMS, the International Monitoring System Division, is responsible for sustaining the global network of monitoring facilities, ensuring that the data comes into the IDC and that the analyst can process that signal data. MFS, we in MFS have developed several components of a supportability analysis capability to help support the IMS sustainment. And we showed a poster of our work to date at the last session of SnT. So I mentioned that we have developed several components of the supportability analysis. Here's a list of some of these. Some of these act at a station or network level. For example, the sparing optimization, whereby we can look at stations or groups of stations to see what is the optimal sparing that they should have to maintain the data availability and to complete their mission. Other analysis components act at the equipment level, for example, the lifetime buy estimation for obsolete equipment. And we have a few other components which we can talk to you about offline. An important aspect is the visual reporting, whereby we can take the results of our analyses and present it in a way which is perhaps more meaningful or perhaps gives better, different insight to the user than just seeing a tabular structure of results. Where we're wanting to go with this, supportability analysis as a service. So we recognizing our stakeholders, our colleagues, and the management in IMS as being our customers, and we are looking to help support them, ultimately leading to enabling a data-driven decision-making for sustainment activities within the IMS. Supportability data includes reliability, availability, maintainability measures. I want to be clear, we are not looking at the signal data which is flowing into the IDC and which our colleagues in the IDC Center are analyzing and passing on to the NDCs. But we are looking at how we can help support the sustainment of the stations so that data keeps flowing in. We are not short of data. We have some numbers here, nearly 300 certified stations, 1,500 sites with sensors, 20,000 plus items of equipment in use, more than 3,000 models, and that equates to more than 60 billion operating hours since certification across all our sites in total. So we are not short of data. But please, don't stop sending your sustainment-related data to us. Keep sending problem reports, CCNs as appropriate. However, this is too much data to really work with traditional rule-of-thumb estimations. So we're looking for something which can cope with this bigger amount of data. And this is where we look to perhaps something like the CRISP-DM framework, which can help support our analysis work. The cross-industry standard process for data mining, it's an open standard process for analysis. It's been around for 20 years, and it's still a very popular methodology for data mining projects. It has 6 steps, which I will talk through. But the beauty of it is it's flexible, we can scale it to fit, and it's application neutral. Other frameworks are out there, but this is a particularly intuitive one to follow, I think. And it helps us to scale the data information, knowledge, wisdom pyramid, ultimately helping to support the idea of data-driven decision-making. So I mentioned there are 6 steps. Here are the first 2, which are key to answering the right question. So first of all, understand the business understanding. What is the project trying to achieve from a business perspective? For us, that is about ensuring that the station sustainment is done in a way which is cost-effective and helps to meet the mission. Once we understand what is the importance, what is the goal of the project, then we can frame the project in terms of scope and importantly set the success criteria, which we will need to refer to later in the process. After the business understanding, we need to look into the data, identify the data required, perhaps do some exploratory data analysis or EDA to understand the quality of the data, what data is perhaps missing, null values, outliers, and understand, okay, how might we deal with these? Perhaps we need to ignore those records or impute a mean or whatever, depending on the nature of the problem. And often understanding the data understanding sends us back to the business understanding as we understand better what is possible within the constraints of the available data. I'm now going to bring an example of our work, which is talking about the data understanding. Perhaps this visual exploratory data analysis can be informative in its own right, and this is a product that we have put together recently and shared with our colleagues. It's the Problem Report Explorer, which looks at the number of problem reports classified as fault failure and the FAMICA classification that's been assigned to them, and we can see straight away, order them by either the duration in days, or we can sort it by the number of tickets, and we start to help our analysts to understand, okay, where can we look first to deal with the problems in the way that brings the most bang for buck. Another example from the same data set, we've enabled the users to enter a search term, in this case lightning, to see, okay, how often is lightning mentioned in the problem reports over time, or perhaps just simply in terms of their impact quantity. The bigger circles here represent the number of, the larger the circle, the more problem reports that have mentioned lightning, and we can see where these are on the map. So again, it helps the user think, perhaps I have a system, an issue with lightning, but perhaps other stations also, and we can take a network level approach towards this. So this is just simply from the exploratory data analysis stage of the process. How do we go further with this? The next step within the CRISP-DM method talks about data preparation. This is where we actually extract that data, transform it, and load it into somewhere where we can actually work with it for the analysis. We perhaps need to clean the data to deal with nulls, as I mentioned, or outliers, and store that data. This is typically the most time-consuming step of this process. Studies have often shown that it takes between 60 and 80% of the time for the whole process, just for this one step. So how can we perhaps make that easier? One solution is perhaps to use a workflow tool to automate the step where possible, or to make it repeatable so that when the next time comes to do a similar analysis, we have some of the tools readily prepared for us. Then finally, we can start modeling, analyzing the data. Here we, as I say, build the model, assess it as to how well that model runs, tune the parameters and refine it, and iterate as necessary. And this may involve returning to the data preparation phase as we discover or some data is not quite fit for our model. We need to refine it better, or we discover more issues with that data. All models are wrong, but some are useful, as the statistician George Box has said repeatedly. Here are two models of the Australian segment of the IMS network. The first, the map. We are all familiar with a map representation of the world, although the world is not a two-dimensional plane. The other on the right, the sparing optimization. This is a supply chain, shows the supply chain, the nose and edges, as from our sparing optimization tool, as parts flow down through the station operators to the stations. This is a much more abstract representation of the Australian segment of the IMS, but this is sufficient for our sparing model as a set of input data for the sparing optimization model. Finally, we look at the evaluation of the model. Did it meet the original objectives? And this is where we refer back to the success criteria that we set in the business understanding. And if so, review the next steps. Perhaps the model is ready for deployment into some software pipeline. Perhaps it is a report to be published to management for them to be able to make their decisions as to what to do with the results of the analysis. And then we go around again with the next piece of analysis. The work doesn't stop. Some further examples of deployment or what we have produced. And I should have mentioned we will have a exhibition area downstairs in the PTS exhibition area, so we can look into more any of these or further of our analyses and results. We can discuss that further in detail. But here we have three examples that I've brought up. The first is where are we? Here, the sparing matrix, which is looking at the results of our optimized sparing tool compared to what we actually have in our inventory coming from DOTS. And this is something similar to what Steve showed earlier as well. We've seen these before. Next up, the equipment age report, which is something which helps the person responsible for a station or the station operator potentially understand how old is the equipment at their station in relation to the expected lifetime of that equipment. So here we can see when the change of color is coming up, this is when it is approaching its end of life, nominal end of life. So if it's all green, it's all light green, it's all good. If it's getting into the dark green, perhaps the responsible person needs to think about taking some action. What that action may be, they may have a variety of options. And finally, this equipment rundown projector looks at the population of a particular model of equipment over time. So here, in this case, this is the in-use equipment increasing over time as the stations are deployed. The spares history as well, and other statuses. And then we look from now, if we cannot resupply spares, and these parts in use will fail naturally as time goes on, and the spares that we have in stock will be consumed. So at this point, we run out of spares, and at this point, we have difficulty supporting that station. So at this point, we need to have some alternative solution in place, either alternative source of spares or perhaps start to implement a new design of station. Again, this is there may be options. So in summary, I would say following the standard approach to the supportability analysis allows us to repeat and reuse the various analytical components and helps to create an integrated system of standard products. Having a standard system also helps greater understanding amongst our stakeholders, the people using the results, the people who are contributing data to us, and it ultimately contributes to delivering supportability analysis as a service, underpinning data-driven decision-making for sustainment activities for the IMS. Okay. And to finalize, I repeat that we have a display downstairs in the IMS exhibition area. So my colleague Peter Benisek and I will be there from time to time. Please come visit and we can talk. Thank you.
Thank you, Danny. Is there any questions from the floor? I have a question. You mentioned 3,000 models of equipment.
Yes.
That must pose a challenge. So
Yes.
what would you like, where would you, just on your gut feel, would you like to see things changing in terms of making that easier for you to model and actually get something that is really sustainable?
From a model's perspective, I would say the greater standardization that there is in the network, the easier it is to model, the easier it is to support, because you have fewer variants. That must be easier. You have fewer exceptions. It's bound to be easier to support as you have the benefit of greater numbers of common parts. I understand that there are maybe arguments for why that is not possible to the nth degree, and the difficulty is finding that sweet spot where you maximize the benefit of both approaches.
Yeah, thank you. And I think we saw that at the first talk this morning from Remy, where we're looking at trying to have some variation within a standard set of products or equipment, I should say. So thanks very much.
Yes, thank you.
Okay. So the second presentation will be given by Joshua Dickey, where he's going to talk about a framework where they dive deep into the data analysis. So.
Good morning. My name is Ray Richards. I'm here with my colleagues, Raul Pena and Josh Dickey, and we're from the Air Force Technical Applications Center, or AFTAC. Together, we'll be presenting the FaultNet. FaultNet is a machine learning algorithm applied to time series data with a goal of data center system status characterization. This representation is structured to detail the progression of AFTAC's status of health monitoring program, from early foundational efforts all the way to this machine learning data analysis application. The discussion sections will elaborate on the need for actionable data, our initial efforts, maturation or the broadening of our status of health data set, the challenges with common static thresholds, the objectives of development of FaultNet, and then finally we'll describe the FaultNet framework and how it can revolutionize the way potential problems are identified on the station or at a site. Initially, our status of health information was limited to the manufacturer's parameters. The limitations were that the data could only be accessed if the full system path was operating. And even then, any remediation would be only reactionary. AFTAC's 2017 SnT presentation identified various equipment problems based on patterns identified in data gaps. How do we get to the left of these data gaps or prevent them altogether? Through fault analysis, various subcomponents were identified as critical for the healthy operation of a network, so we decided to focus more attention in the status of health data we collect from these systems. The necessity was realized for global communication to the sensor location from a networked terminal. Enabling global access meant that we had to provide Ethernet at the borehole. And that was accomplished by installing an Ethernet-based intrasite communications network at the sensor array. This particular is at Vanda that we just completed this year in Antarctica. While collecting status of health data will provide you the foundation of early detection of issues, this is just data. And it must be processed and transformed into actionable performance metrics. Early analysis was accomplished manually, but it was very manpower intensive, and due to this growing scale now of our sustainment data, it's posed a new solution required. We now have to transition to automating the processing of data using threshold alerts and set points, which both have their pros and cons, and Raul will discuss those next.
Thank you, Ray. Good morning. As Ray mentioned, we started a couple of years ago, we started collecting all this new status of health information. And of course, with all this data coming in, it creates a new data set. That data set can be described by the information on this slide. There are 13 standard status of health data streams that we try to collect from each station. This is the bare minimum we want. Some stations have more depending on the equipment that is available at the stations. And at this point, we have at least 2 years of data for the majority of those stations, 148 sensor locations. The data comes from a diverse set of equipment. It could be radios, it could be the charge controllers on the power system, talking about the digitizers, the data acquisition system, sometimes even the NDC databases themselves, where we query and ask for information about data availability, latency, and that kind of information. The tool we use to collect this information is Nagios XI. We do this with a 5-minute resolution, and as recently we're starting, the numbers are about 5,700 service checks and 1,900 host checks, which adds up to about 7,600 data points every 5 minutes. Of course, as Ray mentioned, manual analysis and visualization of this data is prohibited because of the manpower requirements. So we start moving into the automated realm. We have to have a program or a system that looks at this data and generates alerts. And of course, the first step when you're doing that kind of stuff is to set automatic thresholds. That's normally the standard method. What we have discovered, though, is that static thresholds are not, they don't scale well. Even within an array, the same piece of equipment transmitting the same status of health data will require different thresholds. Now, when we're talking about 7,600 status of health data streams, that's an unmanageable number of individual thresholds. So in this example, you can see here, this is a particular station in Kazakhstan, one of our arrays there, that is powered by commercial AC power. And the graph on the far left shows what we want to see. We want to see that constant DC voltage charging the batteries. The one next to it for the left of center, it says okay, because we see some drops in the voltage values. We know they are related to the AC voltage on the power lines. There's really nothing we can do with the power lines. We are aware of it, but if we were to alert on that information to the operators, it's not actionable information. So what you want to do is you want to hide that information from the operators, and the way to do that is we set the thresholds low, otherwise they get alert fatigue and they completely ignore all the alerts. So the problem with that now is that we have set that threshold too low, and we start seeing the short outages and even the extended outages don't get reported on time. So in summary, the static thresholds just don't work at the scale we're looking at. So there has been a lot of advancements in machine learning, neural networks, and artificial intelligence. So we started looking at, can we use that new technology to set new thresholds? Like, well, let's think a little bit further. What if we have the machine learning tell us when there's a problem at the station? And that's how we came about the objectives for FaultNet. We wanted to build a deep learning framework for analysis of status of health data at the NDC or IDC. And we want this to be a binary classifier in which it tells us this is normal, this is not normal. And with that, I'll leave you with my colleague Josh Dickey, who will explain the development and testing of FaultNet.
So as Raul pointed out, doing this analysis in real time has proven to be quite challenging. It's a big data problem, so it's not possible for a human to accomplish this on their own, but it's also proven challenging from a machine learning perspective. This is because the data set's unlabeled. Typically we'd like to have thousands, maybe hundreds of thousands of examples of these outages, but we don't even know what all the outages are before they occur. We're always getting new types of outages. So it's an unsupervised learning problem, and it's further exacerbated by the fact that this is time series data. The typical way to deal with unsupervised problems is to use clustering. But unfortunately, time series clustering has proven to be a massive challenge. There's a lot of research going on right now. We tried out some of those algorithms, but unfortunately, time series clustering usually requires one of two things, either a lot of heavy feature engineering up front or highly precisely aligned time series data, neither of which we have access to. So what are we going to do? After beating our heads against the wall for several months, we decided that if there wasn't a good time series clustering algorithm available, we would make one. And so we present to you today the FaultNet framework, which is basically a set of AI-centric tools that will allow a human expert to rapidly explore, cluster, and even classify unlabeled time series data. We accomplish this through leveraging the power of human-machine teaming. And we do this across dual representation domains. The human expert works with the same familiar time series data they're used to, while the machine is able to do its clustering in this feature-rich encoding space. So how do we build this feature-rich encoding space from the time series data that's application-specific and that typical clustering algorithms can be used on? Well, we developed a neural network architecture which we call the Siamese shift encoder. It takes the raw time series data and transforms it to this Euclidean space where clustering can take place that's low-dimensional, feature-rich, organized, and especially it's optimized to be meaningful to the application. The novel deep neural network architecture we used took a lot of time and tuning, but it borrows aspects from state-of-the-art audio processing, computer vision, and even facial recognition. And in particular, I'd like to just briefly show you how we were able to use a loss function that's been really successful in facial recognition to be able to make these meaningful clusters. So the batch hard loss function is far beyond the scope of this forum here, but briefly, what it requires is that the user provide the algorithm a batch of examples which are divided up into distinct classes. And each class has some set number of examples. And the algorithm, what it does is it takes each of those classes and transforms them onto this encoding space in such a way that all the examples from a single class are grouped closely together while maintaining separation from the other classes. Now, for facial recognition, that's easy because we have a good idea of what classes are. I'm a class, you're a class, everybody's a class. But for this time series data that's unlabeled, how do we give it classes? You know, that's what we're really asking it to do for us. So we can't demand that the user give us pre-labeled classes. Otherwise, you know, So what we did was we said, well, let's implement a little trick. Instead of asking the user to give us precise time windows with class labels, we'll ask them to give us some understanding of the periodicity of class changes. So if you're looking for, solar insolation data, the diurnal change is probably a good one. So what you do is you say any windows that have an overlap that's much less than that window, you consider those to be of the same class, and then that's some overlap parameter that's set. And then the margin is much bigger than the periodicity, and classes that are separated by more than that margin become different classes. Now, there's a lot of theoretical problems with that argument, but it turns out that over the long term, this works very well. And the really great thing about the fault-net architecture is the human-machine teaming. So the clustering algorithm, which even with a modest GPU-driven machine, can build these clusters relatively quickly. The human can then choose a clustering level. In this case, we've chosen 4, plot them in time series, get a sampling of those clusters, and look for 3 things. You're looking for intra-cluster homogeneity visually. So you want to make sure the clusters all look the same within each cluster. And then you want distinction between the clusters. And then finally, the expert, and this is where the expert comes in, needs to make sure that the clusters are meaningful to the application. And there's an iterative process of defining the overlap and margin until you get clusters that look good. And in this case, on our power data, with 4 clusters, it almost perfectly pulled out different classes by voltage and by AC versus photovoltaic sites. But of course, those labels we already had, so that's not interesting. So the next step was to bump up the level of classes. In this case, we bumped it up to 200. And you can see here, excellent visual homogeneity within the classes, good distinction between classes, and best of all, cluster 17 just came out perfectly to solar insolation sites, PV sites, that had no power over the last 2 days. And so using those examples that we extracted using this technique, we built some templates in the encoding space, and then we were able to finally implement our binary classifier for this particular outage. What we did was we took a small data set, hand-labeled it, didn't show it to the algorithm, and then we encoded it into the encoding space, measured the distance between the new samples and our existing templates, and built a simple threshold-based classifier. You can see the receiver operating characteristic curves here. We did it for as few as 1 examples with relatively good performance. And with 3 examples, we were able to get a 64% recall with only a 5% type 1 error rate. So I've blown through a lot of stuff here. And I know there's probably a lot of people in the audience that are interested in this. So we were able, through a lot of work, thank you to Mr. Merker and some other people at Aptec, to make this code releasable on GitHub. So there's a Jupyter notebook that has a huge amount of information on it. And we would welcome you to go and look at it, and in particular, to try it out on your data. Any questions?
Okay. Thank you.
Yeah.
Thank you. My name is Peter Banchak. I work for the PTS. Can you say a few words about the softwares that you use in the backend?
Yeah, so we're using Python, and we're using the TensorFlow API provided by Google. And in particular, we've built, see the Siamese neural network, which I didn't talk about much. I could not find any implementation of it in Keras, which is an API built on top of TensorFlow that's really user-friendly. So I wrote it, and it's available in that code. So if you're familiar with Python, it should be relatively easy to use the code. Yes.
Hi, thank you for the informative informations. I would like to ask, which kind of classifier did you use for your machine learning approach? For example, which kind of classification algorithm?
Are you referring to the classification used in this slide?
For example, random forest or?
Oh, no. Yeah, so it's actually just a distance metric in the encoding space. So the neural network builds this magical encoding space, and then I'm using a KNN algorithm on the encoding space to build my clusters. And then for the actual classifier, I just simply took a threshold of the distance. So if it's within a certain distance, and to be particular, you might be interested, I use the cluster centroid. So using like an example of 10 of these examples of an outage, I took the cluster centroid in the encoding space and measured the distance.
Got it. It was just a hacking, so I guess.
Yeah.
Thank you.
Okay, any further questions? I have a couple of questions.
Yeah.
I wasn't sure, are you still testing this or are you using this in the day-to-day operation sustainment of your network? And the second question is, we saw earlier today on the presentation, more mission, less money. They talked about the 10-second and 100-second data gaps. Have you actually used this and see if you could replicate those same results?
Yeah, so there's two answers there. First of all, no, this is not operational. I'm working currently at Air Force Institute of Technology on my PhD, and I've been kind of just tacking away on this code for the last few days. This isn't part of my dissertation, so it's a side project. But I think our intention is to try and implement it. And regarding the data gaps, I think it's really interesting that you guys brought up in your presentation that that's a vanity metric. There's actually not a lot of correlation between data gaps and equipment faults, which sounds strange, but the fact is that there are a lot of equipment faults that, because of redundancy in the system, never makes it into the data gap. And similarly, there's a lot of data gaps that occur outside the scope of our fielded equipment.
Okay, thank you.
Yeah.
Okay,
Thank you.
Okay, we'll go to the last presentation, and now we're going on to the IDC in terms of the re-engineering of the IDC and the systems engineering that was required for that. So Mark Harris will be giving the presentation.
Great. Okay, so the U.S. National Data Center has been working with Sandia for a number of years on redeveloping their waveform processing system under the SNDC modernization program. We're referring to this new system as a geophysical monitoring system, or GMS. We've also been working for a number of years with the IDC on IDC reengineering to help them define their requirements and needs for their next generation system as well. And we found a lot of overlap in the requirement space between the NDC system and the IDC, as you'd expect. So the NDC has started development, and the U.S. wants to help make the IDC system better as well. So the U.S. is providing as a contribution the GMS software to the IDC. So I'll talk a little bit about the IDC reengineering program and our GMS program. Show a few examples from the software we're developing on the Analyst Workspace, and I'll talk about the 2019 release that's coming up. So on IDC reengineering's been going on for about 8 years or so. This is a fairly long-running, ongoing program. It's now defined as a set of stages, or phases. So phase one was some of the work to enhance or replace some of the major components of the system. So think of the NetVisa Associator as being part of phase one effort. Phase two was where we came in and we started to look at the requirements for the next generation of the IMS system, or the IDC system, defining a unified architecture for SHI processing. And this work we were able to use the work we had done with the US NDC to leverage the requirements and artifacts that we'd developed for the IDC to apply it to for the NDC to apply it to the IDC. So on reengineering phase three, this is defined as the project to develop and deploy this next generation IDC system. And then thanks to the US allowing a contribution, we're able to leverage the work that's happening with the NDC development to provide some components and architecture to the IDC to help with their development. This is hopefully providing a substantial base for the IDC to work with, but there's still a lot of work left to integrate for testing and to develop IDC unique components that aren't being developed as part of NDC. So as I said, we're developing this new system for US NDC modernization. We're calling it the Geophysical Monitoring System. And our vision here is to develop a new system that meets the functional requirements for the NDC, of course, but also meets a set of improved qualities over the old system, and things like maintainability, extensibility, testability, those kinds of things. So the NDC modernization effort is addressing all parts of the waveform processing system. So this is just a cartoon showing the scope of our development. So on the left you can see data acquisition. We're addressing a number of data protocols there, receiving data from the field, making it available to the system, and also forwarding and archiving the data. In the center area, we're covering, of course, automated processing in terms of the pipeline and a set of processing services. This new development is very much service-oriented. So the idea is these services can be independently scaled, independently configured into pipelines as needed by the NDC. On the right, we have the analysis area, where we're also trying to make the analysis part of the system a pluggable and extensible system. And you can see reporting on the chart on the right as well. So this is an area in particular where the IDC has substantial requirements beyond the NDC. They report data in different ways and to different extent than the NDC does. So there will be a lot of IDC unique capability in that area. And then along the bottom we show one of the major architectural components of the new system, this common object interface and the data services. We're trying to make consistent the data access and storage across all the components of the system. And just to highlight, the things that are highlighted in red are things we're calling out as extensible extension points. So things that we're putting specific architectural work into making those kinds of things extensible, like the protocols and acquisition, the services and algorithms. So again, a lot of NDC modernization is about architecting for the set of system qualities that are meant to improve upon the legacy system. So we pay a lot of attention to things like extensibility and patterns for that throughout the system. Maintainability, making it easier and more cost-effective to maintain into the future. Scalability, so we're not just designing to run on a big data center, but it could run in different kinds of configurations. Down to history, so we're working to capture more data as the metadata about the processing results as they're being created, so that can be used in the system. Configurability across the board, so making the system more configurable and more flexible. On down to testability, so we're building in ways to replay data through the system, to replay analyst actions in the system, so that we can do better regression testing and better troubleshooting of the system. So the United States, we found that there was substantial overlap in the requirement space, and the US wants to help the IDC with their re-engineering. So we're contributing the GMS software as an open source project. So posting to GitHub. This includes these common components that are things that are common with the NDC and the IDC. And the scope of this sharing is at the generic runnable system. So we're not specifically putting a lot of work into configuring this for the IDC. And this includes some support from Sandia for the IDC for testing and evaluation. Our plan is to make at least annual open source deliveries of the system. The first was last year in December. This was a really early release of our software, so it really wasn't runnable at that time, external to Sandia, but it's really provided as for review of design and of the software. We're working on our 2019 release right now. This is the software that we just finished in our latest program increment. And this will be a generic runnable and buildable system that we can build and test at the IDC. So just a recap of the timeline. You can see the IDC phases across the top. We've worked on phase 1 is defined to be complete. Phase 2 was a lot about the requirements gathering and some early design and architecture work. And you can see how that lined up with the US NDC. We were doing these basically at the same time and able to leverage the NDC work for the IDC. And now the IDC is going into phase 3, which is their development phase. And again, we're able to leverage the NDC work to help with the IDC. So a little bit about the analyst workspace. We'll show some examples. But first, this workspace is really a framework for installing pluggable displays that the analysts can use. The intention that these are configurable by the analysts. They can, we'll see in the examples, they can rearrange the displays and set it up as it works best for their workflow. And includes things you'd expect like the, a map, waveform display, the list of events that you're working on, various measurement tools. We are using web technologies for the new analyst displays. So that's more familiar to some folks working on the computer, as well as this is just the way a lot of display work is done these days in industry. And there are some advantages to this. It allows a more flexible and somewhat better deployment model. We don't have to deploy software to every user. They can connect to the system with a web browser. And some of those common features like it's usable, user customizable, data synchronized across the displays, those things are built in through this analyst workspace. So just a picture of one configuration of the displays in the workspace. You can see some common things you might work with. On the left is an event list that an analyst could work through as they're working all the events in their interval. You can see a map, you can see a waveform display. It's a little harder to see maybe that this software is running just in a web browser. And in the panels that are showing these displays, there are tabs, other tabs, so things like the locator display, FK, and those things are placed in the panels and tabs, and all that's configurable. How many panels you have on the screen, which tabs are in which panels, how big they are. It's all configurable, and that configuration is stored for the analyst. So just another layout. You can move things around and set it up for how you want to work. In this case, if you want a large waveform display, next to it the FK display showing the FKs and the picks for all the displays for all the picks for the event. We're introducing some new things in the displays as well. And one point about this, we did a lot of storyboarding work early on with analysts both at the NDC and at the IDC to help define these displays, the initial designs of them. And as we go along, we're building the displays and getting feedback on them with the analysts as well. So we had a lot of analyst involvement up front and as we're developing and demonstrating the software. So in this case, this is showing a new element where we have a measurement window that's optional, of course, but it can be used at the top of the waveform display. So it's something that you can highlight a section of a waveform down in the main display, and it'll show a zoomed in and larger version of that waveform at the top. So it might be useful for doing more precise time picks and amplitude measurements and that sort of thing. It's optional. You can do all the same operations in any of these displays, either the measurement window or in the main waveform display, as well as a lot of things are consistent across the system. So if you see a waveform in a different display, like an FK, you can do common things like time picks in that display as well. Another of our new displays, this is FK. So one thing we defined is on the left a set of thumbnails. So these are miniature FKs for all of the picks that are associated with the event you're working on, for instance. An analyst can just select one of those thumbnails to pick which FK they want to work on, and then you get the larger FK window. Down at the bottom, we've added some additional information so we can see the FK beam that's set up for the FK you're looking at. You can also see a trace of the f-stat and the azimuth and slowness in time. So that could be useful for the analyst to set the time window for the FK. Another new thing that we've added was the thumbnails that are more in the center of the display show an FK thumbnail for different frequency bands, so it can help the analyst to quickly pick which frequency band works for the signal they're working on. Finally, a couple of displays showing some of the data provenance that we're collecting in the system. So the one on the top is showing signal detection versions. So we're collecting versions of everything that happens in the system, basically. So in terms of signal detections or arrivals, anytime that signal detection is changed substantially, it's a new version. The analyst can bring up the display to list those versions, and if needed, they could go back to a previous version and work from that. Same thing on the bottom with the QC display, the waveform QC. You can see how the system created a QC mask to start with, and then how analysts changed it over time. So a little bit about our 2019 release. Just a list of capabilities in the system now. You can see under acquisition, we have a number of the data protocols available, CD11, IMS 2.0, etc. Under processing, you can see a lot of the functions are available as processing services in the system that are needed at least for a level 1 analyst activity. So things like waveform QC, filtering, beaming, FKs, signal detection. We're not as far along in event building or the association function, but that's started in this release, and we have an event locator in the system now as well. And under analysis, a lot of the basic displays needed for that level 1 analysis function are available. It's still early in our development. We're about a third of the way through our development activity. So a lot of these functions that we have are just the initial simple algorithms that are in the system. That'll be expanded over time to include all of the different filters in FK, beaming and detectors, for instance. So plans for our 2019 release. Just note that this is the program is planned through 2023. So again, we're about a third of the way through development, but we are planning an open source release at least once per year. For our 2019 release, again, this is what we're calling our PI7 version of the system that was completed in May. We're working on review and approval of that release now, and we expect this to be a buildable and runnable system here at the IDC. And we'll have some support to help the IDC get that going. As far as the content, it's software, of course, the build files and instructions for how to get the system running. Again, it's early in our development, so a lot of things are still immature, especially things that you need to have a real operational system, like consistent configuration, monitoring and control in the system, and especially we haven't put a lot of emphasis yet on performance of the components. We're starting to do that now in our development. So it's just the last comment. There's a meeting next week on IDC re-engineering, on software engineering for the IDC. We plan to have additional presentations on GMS and also a live demo of the analysis tools that we have. If they're not available to go to that meeting, we do have that on a laptop. If you want a quick look at some of the things coming up, you can get with us, and we could probably do a quick demo of that this week. Okay, thank you.
I do have a question and maybe a clarification. So this software is it going to be available to all CTBT participants and member nations without limit?
That's right. One thing with the IDC, one of our things that's really needed by the IDC is open sharing and unencumbered sharing. So this will be completely, what we provide to the IDC will be completely open source under a very good license.
So this, please.
What is the license name? What is the license name?
The
GPA or like license name?
BSD.
And so that's a very important part of this, that we want participation from the very beginning to make this useful for the IDC, but also for individual nations that want to look at this software and use it. So we hope it will be valuable to people individually as well as at the IDC level.
Exactly.
Absolutely, and we encourage that for sure.
And we really hope for that for the IDC in particular, because a lot of the IDC unique functions that they need that aren't part of the NDC development, they need to be developed for the IDC.
Well, thank you very much. We appreciate it.
Thanks.
I'd like to thank all the people that all the presenters and certainly the audience for sharing your concerns and interests and questions. And thank you very much.
Okay, good. That was good. Hey, the things I was going to highlight from that section was obviously the importance of system engineering, whether it's the IMS and the IDC, that it's fundamental if you want to get it right.
Yes.
For optimizing and for sustaining. And we can answer today. Obviously, data is at the heart of, especially the IMS, of the heart of the sustainment. That's the second one. And then the reason I ask certain questions are...
Oh, no, I know. Yep. Filling in holes.
Standardization.
Yes.
I mean, if you really want to get more accurate and be able to do things better, you need to start to standardize. You can't, everything links in. So I was going to just have three main points, and that's good enough.
Okay.
On that. Are you happy with that?
No, I'm happy with it. Yep.
Yeah.
So that's what you're going to turn in?
Yeah.
Okay, because I need to do some work.
Hey?
He had asked me to help with the first session. So that's what kind of the level you want?
It's only supposed to be like three or four dot points.
Yeah.
That's it.
Okay. Well, good. I'm glad you told me that.
Yeah, but you also, I don't have any posters, so I'm done.
Yeah.
You've got posters that you also need to maybe just scan quickly over.
Yeah.
I was thinking timetable tomorrow. When's a good time to meet? Do you have anything scheduled?
I don't.
So we can bring everyone together?
I have nothing scheduled, so, and it's open to when you're free. When you want to get together.
I mean, today's probably not a good day because we want to look at the posters
Right.
around.
Yeah.
So I was thinking Wednesday would be...
Yeah, Wednesday's good.
But let's see when's on Wednesday. So Wednesday...